Good morning.
Good morning.
I see we have something really interesting here.
It's called the Mean Value Theorem, and this is a tool that we use to talk about approximations, in particular Taylor polynomials, something else called L'Hopital's rule. But it's a very key idea in calculus, and so I think it deserves its own video.
Okay, so I think we should start by looking at this function that starts at this point here, AF of A, and goes to BF of B, and this is a piece of it. Draw the line that goes through those endpoints.
So a line would look like this, and it has a slope.
Oh,
So
let's
that means-
compute the slope.
Okay, let's compute the, so slope is rise over run. So the run, well, maybe the rise. What rise
Well,
go from there to there, right?
F of B minus F of A. And the run is here. So that's over B minus A. And we often call that thing M.
Call that M.
Oh,
So I can draw an equation for this. So
Yeah,
this
let's-
here, y, here my curve,
Yeah.
y is equal to f of x. Here this is just the slope, so it's m. And it goes through this point here, a, so x minus a. And it takes the value there of f of a. So that's my equation for the line.
great.
Can I check that, Matt? Is that right?
Sure, I
If
think
I
that.
plug in a, I get a minus a is 0, so I get f of a. Good. If I plug in b, I get b minus a times n. That cancels this b minus m, so I get f of b minus a plus f of a. That's f of b. Good.
So it all works. So it's the right picture. Now, what we notice is if we start looking at the tangents here, there's going to be a place where the tangent to the curve is got the same slope as the line.
And you can sort of see if I took this line and moved it up until it's just barely touching, I get a line here. Now, what do we know about tangent lines? How's that related to f? What's its slope?
Sure, it's the slope right here has got to be equal to the slope right there,
So
in the
this
middle
is-
somewhere
This is the derivative, right?
of some point C.
So what we're saying is, if you look at this picture, f prime at c is equal to this slope m.
Right, so
So-
we can write that down.
So
We have
I'm going to
it.
write down, this is our theorem then. It says, given a situation like this, the slope, f of b minus f of a over b minus a is equal to m. Oh, that is m. Is equal to,
F prime of C.
so that is the mean value theorem.
Now, Michael, you said we take this and we move it up like that. So what we'd like to do is look at this. So do you have pink?
Pink.
So we have this little face here that I'm going to draw.
Okay.
And so we're going to represent this face by grabbing the face and like a brim of a hat and make it horizontal.
Right.
And then we'll be able to see what happens next.
And in fact, I think you can see exactly how to do that. If you take the distance from here to here, that'll give you something that flattens out, because here the distance is 0, here the distance is 0, and so you'll flatten it out to something that looks like that.
Yeah, well, let's look at that now.
I'm going to give that a name, even though we don't know the formula for it yet. Call it h.
Sounds good.
So
Well,
can I write out h?
subtract the two curves,
That's
one
right. So you
being
got
a
the
straight
top
line.
curve. The top curve was f of x, right?
Yeah. And the straight line, you have it because we have the slope and the equation here.
So let me, okay, I'm going to stop using m. I'm going to use this. Or should I use m?
No, you can use that because then we can see, we don't have to remember what it is. It's right in front of us.
F of b minus f of a divided by b minus a, so that's our m. It gets multiplied by x minus a. And then we add up f of a.
Now that you have that, we want to check that h at A equals h of B is 0.
So let's compute x of A. This is f of A minus. Okay, this is some number, but A minus A is 0.
So this is
0, right?
plus f of A, so that's 0. As it should be right here from the graph.
Right, so this is 0. Let's try h at B now. This is, of course, f of B. Now I have to work a little bit harder. I get f of B minus f of A divided by B minus A times B minus A plus f of A. Well, we notice this cancels that.
And the f of A's cancel. And now we got f of B minus f of B, which is, of course, also 0.
So this really is h.
And this point here at the top will be, C would be, if you rotate it, this would be flat.
That's exactly where h prime is equal to 0. So, why do we know there's a place where h prime is equal to 0? Well, assuming everything is differentiable, if f is differentiable, this line is differentiable, I subtract the 2, I get a differentiable function. The function going from 0, A to B, it goes from 0 to 0, so it's got to have either a maximum or a minimum. I mean, if I drew a different picture, h might look like this, and then we might have to look at its minimum. But at minimum or maximum, these functions
What would happen if this function wasn't curved? Well, then it would be a straight line, so it would be parallel, or it might intersect at one point.
Or it might be parallel, and then this would be flat, so the derivative would be 0 everywhere.
Right.
So we can have lots of places where the derivative is 0, but we know we have at least one place. We'll call that place C, okay?
Yeah.
And then let's see, so what happens if h prime is equal to 0? Well, okay, so here is h. Can I compute the derivative right down here?
Yeah, sure.
H prime of x. So this is going to be f. It becomes f prime minus, okay, here's the only place that x shows up.
Yeah.
Its derivative will be 1, gets multiplied by this. So this is f of b minus f of a over b minus a. And we know at some point c, this is equal to 0.
At x equals c.
So I'll put in a c here.
And I'll C there. And then you have the famous line from the U.S. national anthem. Oh, say, can you see?
Oh my. And there we go. This is our formula. The difference, f of b minus f of a or b minus a is equal to the derivative at some point c.
In the
if
middle.
This is equal, these two guys are equal.
So how can we use that?
Lots of places. So, okay, here's a cute little example. We've seen this stuff that sine x, we know for x small, is approximately equal to x. Okay, we can actually be more precise. We can actually say sine x divided by x is very close to 1. In fact, as x gets closer and closer to 0, sine x over x gets very, very close to 1.
We showed that geometrically earlier.
We did see that geometrically. Let's see how the mean value theorem comes. I feel like I'm running out of space here, but you know what? I bet you I can put it on here. If I put sine x over x, now that's the same thing as sine x minus sine 0, right?
Yeah.
Because sine of 0 is 0. X is the same thing as x minus 0. And you look at that picture and say, hey, that looks a whole lot like this picture. F is sine, A is x, no, A is 0, B is x, right?
Yeah.
And so from this is equal to the derivative of sine at some point c. What's the derivative of sine?
Cosine
Cosine
of c or some,
of c, yeah.
at some point.
So c has to lie between 0 and x. But cosine of c, we know from our linear approximation, is 1 plus 0 times c.
Right.
So it's very, very close to 1. And in fact, we haven't talked in detail about errors, but the point is the error, the difference between this and this, is always going to be, it's going to get smaller and smaller as x gets close to 0, and it eventually vanishes.
And we saw that actually geometrically.
We saw that geometrically. So there's a quick little application of the mean value theorem.
Well, let's look at more applications
Next time.
next time.